Hey, what's up, everyone? Happy Monday. We're back doing some linear algebra, talking some more about the minimal polynomial of an operator on a finite dimensional vector space. So here's the gist of it. Let's do a quick recap. Here's what we were talking about. So given a vector space V with dim v less than infinity, that is a finite dimensional vector space, and an operator on that vector space, that is a map from the vector space to itself, we showed there is a unique monic polynomial P. I was going to say with, but I'll say such that P of t is the zero operator. Okay, so the idea of it is that uniqueness, monic, polynomial, this thing, there's three parts basically. So we can find a polynomial so that if you plug the operator in, you get out the zero operator. Okay, so basically, essentially it says that, hey, you can take an operator, you can do it some number of times, you can put together some scaled copies of doing the operator a number of times and somehow get the zero operator. All right, you can do so with a polynomial of as low a degree as possible. After all, if you can do it with any polynomial, then you could pick the one that's as low a degree as possible. Okay, cool. Then we could take the first, the leading coefficient, that is the term next to the biggest power of the variable in the polynomial, and divide the whole thing by that. Then we get a monic polynomial. That is a polynomial which has 1 as its leading coefficient. And it turns out that this polynomial is unique. That is, it is the unique polynomial of lowest degree such that P of t is 0. I should say unique monic polynomial P such that this and the degree of P is as small as possible, i.e., minimal. This is the minimal polynomial of t. So there is this special fancy polynomial that has degree as small as possible, makes P of t equal to 0, and is monic. This guy is unique. So basically it says corresponding to every operator, there is this special polynomial. All right, we'll see what this does for us. Last time we saw some cool stuff. We saw the zeros of the min polynomial of t were the eigenvalues of t, potentially repeated up to their multiplicity. Okay, cool. So we haven't talked about the multiplicity of an eigenvalue yet. Eigenvalues of t, I'll say potentially with repetition. Okay, cool. So today, let's start off by showing this fact. We'll suppose that v is finite dimensional, t is an operator on v, and q is a polynomial over the underlying field. Then what we're going to claim is that q of t is the zero operator if and only if q is a polynomial multiple of the minimal polynomial of t. Okay, this feels reasonable. After all, the minimal polynomial is the unique monic polynomial of lowest degree such that it zeroes out t. So if something else zeroes out t, it either has to have higher degree or it has to not be monic. In either case, it's a multiple. All right, let's get into it. So here's the gist. Let's run through the proof. It's not too bad. It's pretty straightforward. It just relies on a little bit of polynomial long division. So suppose P is the minimal polynomial of t. Okay. I'll say if q in pf is such that, terrible t, let me fix that, such that q of t is the zero operator, then we can do some division. So then doing division, there are polynomials. Let's call them S and R, such that Q equals PS plus R, with the degree of R less than the degree of P. This is essentially exactly the same thing as doing regular old long division. That is like, 5 is 2 times 2 plus 1. That is, the remainder always has to be less than the thing you're dividing by, right? That's all it's saying. It says, hey, Q, we can divide it by P. So there's some number of P's, and then there's a remainder, and the remainder has to be smaller than P, at least in terms of its degree here. All right, cool. Nothing too crazy. Then, from this, Q of t, well, that's the zero operator, which is then again equal to P of t, S of t, plus R of t, which is just the zero operator times S of t, plus R of t, which is then just R of t. Oh! So R of t is 0, and the degree of R is less than, I'll just write it as deg, how about? Deg R less than the degree of P. So by minimality, R is the zero polynomial. That is, Q equals PS. Oh, okay, so here, just think about this. Since we can plug in t and we get 0, well, that's Q of t by assumption, which is P of t times S of t plus R of t. Well, we know P of t is the zero operator, so we just get R of t. All right, R is a polynomial of degree strictly smaller than P. So it may not be monic, but either way, we get R of t is equal to the zero operator. If it's not monic, we could just multiply by a scalar, that is 1 over its leading coefficient, and get a monic polynomial of lower degree than P that zeroes out t. But this would contradict the minimality of P. So by minimality, the only way that R could do this is if it's the zero polynomial. Ooh, okay. That's pretty wild there. All right, so now Q is equal to PS. That is, Q is a polynomial multiple of P. It's P times the polynomial S. Oh, okay. Conversely, suppose, I'll write it this way. I'll suppose Q is equal to PS for some polynomial S in PF. Then, watch this, then Q of t is equal to P of t, S of t, which is just 0, S of t, which is just 0. Oh, okay, so you got it both ways. If Q of t is 0, Q is a polynomial multiple of the minimal polynomial, and if Q is a polynomial multiple of the minimal polynomial, well then if you plug in t, you get a polynomial evaluated at t times the minimal polynomial evaluated at t. The minimal polynomial, if you evaluate it at t, you get out the zero operator, so that product's going to be 0. Bada boom, we're done. Huh, Cool. All right. So what this says is that anytime you zero out t using a polynomial, then what you're really doing is you're using the minimal polynomial and maybe just multiplying it by some stuff. Kind of nice. All right. So it sort of says we don't have any pathological cases. That is, we don't have some way of getting a polynomial that is 0 but is not divisible by the minimal polynomial, something like that. It's actually a kind of nice factoring result. Okay, so we can do some nice stuff with this. So here's the idea of it. Let's say that V is a finite dimensional vector space, as usual. T is an operator on V. And now here's the new thing. Let's suppose that U is a subspace of V that is invariant under T. Then what our claim is that the minimal polynomial of T is a multiple of the minimal polynomial of T restricted to U. Okay, here's the idea. So the basic gist of it is saying that, hey, you can get the minimal polynomial of T, and then if you've got an invariant subspace, you can restrict T to that subspace and get an operator on the subspace. Okay, now the operator on the subspace should somehow be compatible with the operator on the whole space. After all, they're equal to each other for things in the subspace. So their minimal polynomials should hopefully play well together, and it turns out that they are. Basically, it says that, hey, you can understand what the minimal polynomial is by understanding the minimal polynomials of T restricted to invariant subspaces. This is really nice considering the fact that the zeros of the minimal polynomial are the eigenvalues of T. That is, if we're trying to understand what T does, then our whole goal has been to break down the vector space into small invariant subspaces where T behaves a little bit more simply. Okay, fair enough. On all of those small invariant subspaces, we can get the minimal polynomial of T restricted to that subspace. And then putting them together, we should get back the minimal polynomial for all of T. This is kind of our roadmap for where we're going to go. All right, let's prove it. So let P be the minimal polynomial of T. Hence, PT is the zero operator, and PT applied to a vector V is just the zero operator applied to V, which is just the zero vector, for all V and big V. So, P of T applied to U is equal to the zero vector for all U in U. Okay. Oh. Hence, P of T restricted to U is equal to the zero operator on U. So that's the zero in LU, essentially. Maybe I should be somewhat clear here because T restricted to U. So T sends V to V. T restricted to U sends, not equals right there. This sends U to V. So what I should really say here is not that this is the zero operator in LU. This is the zero map from U to V. And so maybe what I should really do is I should say T restricted to U with some special caveat. Like I should call it like T tilde or something like that. Restricted to U, which sends U to U instead of U to V. But just to kind of avoid all this messiness. Let's avoid this mess just by thinking about this as if it was the map that sends U to U as opposed to the map that sends U to V. So that way I don't have to name a separate map. All right. So if we think of this as an operator on U, then when I plug it into P, I get out the zero operator on U. Okay. Thus, by the previous result, P is a polynomial multiple of the min poly of t restricted to u, where once again, there's a little tiny bit of abusive notation right here. But if we just implicitly accept that t restricted to u also we're changing the codomain and not just the domain, then everything's fine. So turning t into an operator strictly on u, we can get a minimal polynomial. Since the minimal polynomial will just zero out that t restricted to u, then since p takes the t restricted to u and also sends it to 0, then this p must be a polynomial multiple of the minimal polynomial of t restricted to u. Bada boom, not too bad. Okay, so things are looking pretty good in terms of the plan we have of breaking down our vector space into small invariant subspaces where it's easier to understand what our operator does. We have this nice tool, a minimal polynomial. Its zeros are the eigenvalues of t, which, as we've talked about before, are closely associated to the small invariant subspaces that we're going to break our vector space down into. And if we restrict t to those invariant subspaces, we're just factoring the minimal polynomial. So this is really nice from an algebraic sense. Let's keep going. Okay, so what can we do with this minimal polynomial? What does it give us? Well, a lot of different things, and we're going to use it quite a bit in the weeks to come, but here's one that's real easy. So, supposing yet again that v is finite dimensional and t is an operator on v, the setup for having a minimal polynomial, then here's the claim. T is not invertible if and only if the constant term of the minimal polynomial of t is 0. So, this is kind of crazy. It's sort of hard to check if something is invertible. Here's the wild thing. All that information is contained in a single number in the minimal polynomial. Oh man, this minimal polynomial is pretty neat. And in fact, think about something really quick. Do you remember anything from regular old linear algebra where having something non-zero implied invertibility? Maybe something that determined invertibility? Maybe something like the determinant? Perhaps there's some connection between the constant term of the minimal polynomial and our old friend the determinant, which we have not yet talked about. So, kind of interesting. We'll get back to that pretty soon. Let's do the proof of this one. So proof. Okay, this one's actually really easy. It's just one of those strings of if and only ifs, which is one of my favorite types of proofs. Okay. Let P be the minimal polynomial of T. Now, T is not invertible if and only if 0 is an eigenvalue of T. That is, since T sends v to v, it fails to be invertible if it fails to be injective. And the only way it can fail to be injective is if it sends something non-zero to 0. That is, if tv equals lambda v, where lambda is 0. That means tv equals 0. So the only times that t is not invertible are when 0 is an eigenvalue of t. Okay, but this happens if and only if 0 is a 0 of p. After all, the zeros of the minimal polynomial are the eigenvalues of t. But hey, this happens if and only if p of 0 equals 0, but that means the constant term of p is 0. Oh, whoa, look at that. Okay, you plug in 0, everything that has a variable next to it gets zeroed out, and so you're left only with the constant term. The constant term has to be then 0 if p of 0 is equal to 0. Whoa, very cool. Okay, so just in a single term of the minimal polynomial, we have all the information we ever want about invertibility. Man, this minimal polynomial is kind of fancy. Okay, let's use the minimal polynomial to show the following fact. We're going to show that every operator on an odd dimensional vector space has an eigenvalue. Whoa. We've previously shown that every operator on a finite dimensional complex vector space has an eigenvalue. But here, we're just going to do it in general for any old odd dimensional vector space. To get there, we'll need one kind of technical result. So let's say, hey, let's let the field be the reals and suppose that V is finite dimensional. Now we're going to take an operator on V and two real numbers, B and C, with B squared less than 4C. Then our claim is that the dimension of the null space of T squared plus BT plus CI is an even number. So let's talk about it real quick. This is, if this seems like, why are we doing this? That's totally fine. This is just like a lemma that will let us get to the next one. That is, in the next proof, the thing we want to show, that every operator on an odd dimensional real vector space has an eigenvalue. To get there, we're going to need to use the fact that the dimension of the null space of this guy is an even number. All right, so here's the simple way to think about it. Basically, over the reals, everything that doesn't factor has a quadratic term that doesn't factor. So that is, if you have, linear terms, then those things factor, but the kinds of equations over the reals polynomial equations that don't have solutions are things like x squared plus 1 equals 0, right? So quadratics. All right, fair enough. So if we take a quadratic, we look at its null space, getting a dimension that's an even number tells us that it cannot be the whole space if the whole space has odd dimension. So that's why we'll prove this. You'll see it better in the next proof, but for now, let's just go through and do this kind of technical little piece that will help us out a lot in the next proof. So instead of just doing it all at once in the next proof, we'll prove this little sort of ancillary result first, then we'll use it in the next proof and make it a little bit easier. So just remember, basically all we're doing is we're showing that the dimension of the null space of a quadratic is an even number. Okay, this will let us show that every operator on an odd dimensional real vector space has an eigenvalue. Okay, cool. So let's get into it. Recall that the null space of P of T is invariant under T for any polynomial P over the field. In this case, I guess the field will be R, so maybe I can just write PR there. So we proved this before. Now we just said basically, hey, null space of polynomial operator is invariant under the operator that you're plugging into the polynomial. All right, cool. Now, here's what we'll do. This is kind of hand-wavy, but just to skip some technicalities. If necessary, replace V with the null space of T squared plus BT plus CI and T with T restricted to the null space of T squared plus BT plus CI. So that, here's the idea. So that, well, here, let me say this. So that we are only dealing with this null space. That is, if this null space is not equal to all of V, then just pretend that it was and restrict T to an operator on that invariant subspace. Does that make some sense why we might want to do that? The idea is that we're just trying to make a statement about the dimension of this guy. Yeah? So we don't care about the rest of V. Let's just pretend that V was, like, this thing is all of V in the first place. If it's not, replace V with this thing. Oh, okay. Easy enough. So now once we're there, this lets us assume we'll say t squared plus bt plus ci is equal to 0. Here's the gist of it. If you restrict t to this null space, then we, sorry, I'm getting tongue-tied. Here's what I'm trying to say. I just don't want to have to write t restricted to the null space of t squared plus bt plus ci every time, because this takes way longer to write than t. So we'll pretend that t was this already by assuming that v is this. If it's not, replace v with this and replace t with t restricted to that. And then I can just use t instead of writing t restricted to the null space of t squared plus bt plus ci every time. So in that case, this thing is 0. Why? Well, because on the null space of t squared plus bt plus ci, it sends everything in there to 0, right? The null space of t squared plus bt plus ci is all of the v's in v, such that t squared plus bt plus ci applied to v is equal to 0. Since we are taking v to be null t squared plus b t plus ci, if it is not already. Okay, so it's the 0 operator. Okay, does that make some sense? I'm being a little bit loose with my notation here, but like I said, we're just doing it so I don't have to write t restricted to the null space of t squared plus bt plus ci, which is a mouthful to even say, let alone write, every single time. All right. Hence, what we need to do now is show that the dimension of v, which is the null space of t squared plus bt plus ci, since we've replaced v with that, is even. We want to show the dimension of the null space of t squared plus bt plus ci, which is, we're saying the dimension of v, is even. Okay, to do this, suppose lambda in the field, which is r, and v in v is such that tv equals lambda v. Okay. Then, watch this. 0, well, that's t squared plus bt plus ci applied to v, right? Okay. Since this is the 0 operator on the on its own null space, and we're assuming that v is in that null space, okay, this just turns into, well, apply t to v, you get lambda v. Pull the scalar out and apply t again, you'll get lambda squared v. Lambda squared v plus b lambda v plus c v. Okay. Little tiny bit of grouping here together. I'm going to make this claim. This is a little bit of like a completing the square, if you recall this from some algebra. Lambda plus b over 2 squared plus c minus b squared over 4 v. So, completing the square, if you've forgotten all about it, all it is a way to square stuff out, right? You want to write it as a square with some extra little bit right here. Okay, so we've got a square, and then we've got our plus c. I have to get rid of whatever that extra term is from here to make it work out nice, but there we go. Okay. Since we have assumed in the statement of this theorem that b squared is less than 4c, here's what we'll get. Since b squared is less than 4c, 0 is less than 4c minus b squared, and dividing by 4, 0 is less than c minus b squared over 4. So, this right here is a positive number. That is, I've got something squared. Smallest it can be is 0, can never be negative. Then I've got something here that is greater than 0. So I got something that can be at most, or at least 0, and something that's bigger than 0. I've got something bigger than 0. So it's a positive number. All right. Hence, v is equal to 0. Okay. So t has no eigenvectors. Oh, okay. So we started out by saying suppose lambda is an eigenvalue of t. Well, then what we got back was that v is 0. So it has no eigenvectors, hence no eigenvalues. Ooh, weird. Interesting. Okay, now what can we do with this? Okay, so we got no eigenvectors. Now the next piece is kind of silly. At least it's sort of technical. Let me pop a little bit of extra room over here. So I'll continue right here. Okay. Proof continued. Okay, here's the deal now. So what we're going to do is say, let U be a subspace of V that is invariant under T. Okay. Moreover, suppose dim U is as large as possible. That is, if T has a bunch of different subspaces that are invariant under it, let's pick one that's got as big a dimension as you could possibly have. Maybe there are multiple ones that have high dimension, but have the highest dimension. But let's just pick one of those ones. It doesn't matter which one. We've picked one. Okay, cool. Now here's what we're going to do. What we're going to do is we're going to say, let's take it to be as large as possible. And since what we want to do is we want to show that the dimension of V, which remember, we're saying V is the null space of t squared plus bt plus ci. We want to show that the dimension of V is even. So basically the gist of it is well, actually I should be careful here. The gist of it is that the largest the dimension of U could be is V, since after all, T, a operator on V, has V as an invariant subspace. So let's add a condition here. I think I forgot to write this. So let's suppose the dimension of U is as large as possible, while remaining even. So what we'll end up showing is that you can get all of V. This will say that the dimension of V is even. So we won't start by assuming that the dimension of V is even, since that would be assuming our conclusion. We'll just start by taking a subspace that has dimension as large as possible and is even dimensional. Now, if U is equal to V, we are done. If not, let W in V be some vector such that W is not in U. Okay, so if you get all of V, you're done. Now V is even dimensional. If you don't, let's grab some vector that's not in U. Okay, this is easy to do. If U is not equal to V, there's something outside of it. All right, let's let big W be the span of little w and tw. Okay. Then W is invariant under T. Why? Since, here's the trick of it, well, if I apply T to W, then I'll certainly get back TW, so that's in there. Now if I apply T to TW, let's see what happens. T of TW, this is T squared W, but T squared W is equal to minus BTW minus CW. And this comes from the fact that T squared plus BT plus CI is the zero operator, which means that t squared is equal to minus bt minus ci. Oh, okay. So t squared w is minus btw minus ciw, which is just minus cw. Oh, okay. So this is just a linear combination of tw and w. Oh, okay. So you apply t to tw, and you get back something that is in w. You apply t to w, you get back something that's in w. So any linear combination of those two guys, which is everything that's in the span, is also going to be in w after you send it through t. Nice. So it's invariant under t. Okay. Now, moreover, since t has no eigenvectors, tw is not equal to lambda w for any lambda in the field. And this means that tw is not in the span of w. And from that, we can say the dimension of w is 2. That is, this is a linearly independent list, w and tw. Okay, cool. All right. Now, the dimension of u plus w, well, that's equal to the dimension of u plus the dimension of w minus the dimension of u intersect w, right? Okay. But hey, this is just equal to the, wait a second. This is the dimension of u plus 2, and their intersection is 0 since w's not in there. Oh. Okay. So, and u plus w is an even dimensional subspace that is invariant under T, contradicting the maximality of U, or the maximality of, I'll say, dim U, since we picked U to have the largest dimension. Okay, so U equals V must have been the case. Oh, okay. So we said, hey, let's take U to be a subspace of V that's invariant under T. Moreover, let's suppose that its dimension is as large as possible while still being even. Now, if U is equal to V, we're done. If not, what we showed is that we can get an even higher dimensional subspace that is invariant under T, which contradicts the idea that we chose U to have a dimension as large as possible while remaining even. So it must have been the case that U is equal to V. Oh, okay. Now, what this has shown is that the dimension of the null space of T squared plus BT plus CI is even, since V we took here to be the null space of T squared plus BT plus CI, mostly just to save ourselves a little bit of writing. Okay, cool. Let's go in to the final result and show that every operator on an odd dimensional vector space has an eigenvalue. Okay, finishing it off. This is kind of a fun one. So we're going to show that every operator on an odd dimensional, and I guess I should add here, real vector space has an eigenvalue. Okay, proof. So, bada boom. Let's do it. We do induction. Base case. Suppose the dimension of V is equal to 1. Then, if T is in lambda V, all we have to do is notice that T, if it sends a vector space of dimension 1 to itself, all it could ever be doing is multiplication. I'll say this. I'll say even easier than saying it like this. I'll say that if the dimension of V is in 1, every non-zero vector V in V is an eigenvector of T, since TV is equal to lambda V for some lambda in R. That is, if you're just sending a vector in R, a number, to another number in R, then that number is a multiple, right? i.e., if TV is equal to W, then, since we're just getting things out in our field, TV is equal to W over V, since V is just a thing now in the field. Oh, okay, cool. So we got the base case down. It's got an eigenvalue. Okay, cool. Inductive step. Suppose every operator on an odd dimensional vector space with dim V less than some n, or less than or equal to some n, has an eigenvalue. We show this implies any operator on an odd dimensional vector space of dimension. So with dimension of V less than or equal to n, if n is odd here, dimension dim V equals n plus 2 now. Since if we did n plus 1, we get something even, right? Okay. Now, to do this, all we got to do is take some nice facts about polynomials. Okay. Let P be the minimal polynomial of T in LV. So we take our operator, we get our minimal polynomial. If P is divisible by lambda minus Z for any lambda, or even I'll write it as, how about I'll write it as a Z minus lambda just for convenience, or even I'll use X instead of Z. So I'll write it this way. I'll say by X minus lambda to keep everything monic. Then P of lambda is equal to 0, and lambda is an eigenvalue of T. Okay, so if P is not divisible by X minus lambda for any lambda, then I'll write it this way. P of X is equal to Q of X times X squared plus BX plus C with, and here's the piece that is important, with B squared less than 4C. Since X squared plus BX plus C equals 0 for quadratic formula, X equals negative B plus or minus square root B squared minus 4AC all over 2A. And X is not in the reals when b squared is less than 4c. Here I wrote the a here. The a here, notice, is 1, so I can just get rid of it, right? If a is the thing next to x squared. This is 4c over 2. Oh, okay, cool. Oh, okay. So if p is not divisible by this, then p of x is equal to some quadratic times some other polynomial. All right, cool. Now, the important piece here is the following. So, 0, well, that's the minimal polynomial evaluated at t. It's a 0 operator. That's how the minimal polynomial is defined. It's the unique monic polynomial of lowest degree such that p of t is the 0 operator. Okay, well, this is q of t times t squared plus bt plus ci. Okay, now, hence, q of t restricted to the range of t squared plus bt plus ci is equal to 0. Okay. Why do we want this to happen? Or what does having this mean? Well, if I plug in some v, then I'll get qt of t squared plus bt plus civ. Okay. If t squared plus bt plus civ is some other vector and not 0, then qt of that vector is 0. Okay, so that gives you something in the null space of qt, right? Okay, let's think it through a little bit and let's keep going. So, since the degree of q is less than the degree of p, and p is the min poly of t, the range of t squared plus bt plus ci, I'll put parentheses there, is not all of v. Otherwise, q of t would be the 0 operator on all of v, but this can't be the case because q has degree smaller than p. And if that was the case, then I would have something of degree smaller than the minimal degree, and I would get out 0 when I plug in t. So it's a contradiction to the minimality of the minimal polynomial. Okay, so it can't be everything. All right. By the fundamental theorem of linear maps, the dimension of v is equal to the dimension of the null space of t squared plus bt plus ci plus the dimension of the range of t squared plus bt plus ci. Oh, so much writing here. Okay, now we know since dim v is odd and dim null t squared plus bt plus ci is even, that's what we just showed with our little lemma we just proved right before, dimension of the range of t squared plus bt plus ci is odd. So our inductive hypothesis applies to, and I'll write it this way, t restricted to range t squared plus bt plus ci. Oh, okay. Oh, nice. Remember, the null space and range of a polynomial evaluated at an operator is invariant under that operator. So this is an invariant subspace of t, and this thing is an odd dimensional vector space, so t is an operator on it. Okay, or t restricted to that is an operator on it. And hence, t restricted to the range of t squared plus bt plus ci has an eigenvalue. And so then does t. Oh, okay. So that t restricted to something has an eigenvalue. You've just shown that t has an eigenvalue as well. Nice. Okay, that's a kind of silly proof. In some ways, this is it feels overly complicated, but here's the whole picture again. Wow, did we do some writing. The idea is we just did induction. If we're one-dimensional, we're just sending numbers to numbers, so the eigenvalues are extremely easy to compute. Take any non-zero vector, map it through, you'll get out some number. Now, the eigenvalue is that number divided by the thing you plugged in. Okay, cool. So, all we have to do is do the inductive step. We suppose it holds true for all vector spaces of a smaller dimension. Sweet. Now we take the dimension of v to be the next larger one, and assume it's odd, of course. Now if p is divisible by a linear term, just x minus lambda, then we get an eigenvalue. If it's not divisible, then there's some quadratic that doesn't factor any further. This only happens when we're in the situation that was like the lemma we just proved. So we can say that the null space of t squared plus bt plus ci is even. Using the fundamental theorem of linear maps, this means that the dimension of the range of t squared plus bt plus ci has to be at least 1. It certainly can't be 0, because otherwise the dimension of v would be even, and we've assumed it's not. So this means that the dimension of the range of t squared plus bt plus ci is odd, and the range of t squared plus bt plus ci can't be all of v. Okay. And that the fact that it can't be all of v just comes from the fact that p is the minimal polynomial, and when we do this little bit of factoring, that would contradict it, the minimality of the minimal polynomial, how small its degree is, right? Okay, so we just take t restricted to this invariant subspace, which is an odd dimensional vector space with the dimension smaller than the current vector space's dimension. And now, t restricted to that, well, the inductive hypothesis applies. That guy's got an eigenvalue, and so does t then. Cool. So, every operator on an odd dimensional real vector space has an eigenvalue. Every operator on a complex vector space, finite dimensional, has an eigenvalue. It seems like the only place where things could go wrong at all are on even dimensional real vector spaces, which if you think about it, since the complex numbers are just kind of like 2 copies of the real numbers, the only way things can go wrong is if we're basically looking at the complex numbers, but just forgetting about some of the complex numbers, right? Even dimensional real space is a complex space of half the dimension, except we're just forgetting about some of the scaling terms. All right, this makes some sense. So basically things go wrong when we're basically in a complex space, but we're just not pretending we're not. This is kind of cool. All right, we'll talk about it more next time, but let's call it quits for today. Have a good one.